Ladies and gentlemen, welcome to It's Rainmaking Time. This is Kim Greenhouse. It's so neat to be in the Starship Enterprise studio today in Burbank with Bruce Barker. It is exactly where I started in radio. The first show for It's Rainmaking Time started with Bill Cox on dowsing and primary water. And it is no accident that in November 2013, we are still focused on water. I think we've done about 13 segments on water with different scientists and pioneers from around the world. I have a great love of this subject and a dedication to it in every aspect of it, and so we are really going to have a robust conversation today. Our guest is prominent. He is the professor of bioengineering at the University of Washington, editor-in-chief of Water. He has written the blockbuster new book, The Fourth Phase of Water, Beyond Solid, Liquid, Vapor. Some say it's the most significant scientific discovery of the century. He travels incessantly. For me to get a hold of him, I must tell you, it was harder than getting a hold of one of the presidents of the United States. He may not think so, but I know so. This new book may change the way we understand water. I'm going to ask Dr. Gerald Pollack to come forth and talk to us about the exclusion zone of water. He builds a new framework for water. Dr. Pollack has won a very prominent award called the Pryigine Award in 2012. Ilye Prigogine was a brilliant physicist, one of the great thinkers of our day in the area of whole systems and systems in general. He understood chaos and how systems work and interact like few people on Earth, and to be given this award is very, very significant. Ladies and gentlemen, welcome Dr. Gerald Pollack to It's Rainmaking Time. Good morning.
Good morning, Kim, and thanks so much for the invitation. I'm really delighted to be with you.
Well, thank you very much. I think one of the first things I want to do is thank you for acknowledging several of the pioneers that have come before you. In particular, I just want to say a heartfelt thank you for mentioning Dr. Jacques Benveniste, one of my favorite people who suffered so much in attempting to bring us the understanding that water has memory. And I think when you're a pioneer and you mention the people that have come before you, just the trials and tribulations, it's a very good thing because the highest level of knowledge that you have couldn't have come from all these people that have come before us. I really appreciate you mentioning him and the others that you mentioned.
Well, thanks. Jacques was actually a friend of mine. He had an untimely death, really too bad, because he was a really major figure in science. Of course, he was reviled by many of the establishment for staking a claim that water has memory, which seemed preposterous to so many people, and still today seems preposterous. But Jacques was ahead of his time, and the experiments that he did have been repeated time and again successfully with similar results. And just last week at our annual water meeting, this time in Bulgaria, there were multiple presentations not only confirming what he found, but actually approaching a mechanistic understanding of what happens when you do serial dilutions and how the information is retained. So Jacques is a hero, and he's been a hero in my books, and I think he'll prove to be a hero in the future, although reviled at present and laughed at as being part of the biggest scientific joke in recent history.
I thought it was also great that you wrote extensively and prepared your readers in the book, The Fourth Phase of Water, Beyond Solid, Liquid, and Vapor, about this need to build a framework in science, how the new paradigms and new ideas are dangerous and not really welcomed and are disruptive. I think it's critical.
It certainly is. People outside of science think that science is really innovative and searches for new truths. In fact, it's quite the opposite. Scientists are actually quite conservative in their thinking, and they feel comfortable in areas with which they're familiar. Scientists like to spout off what they think they know, and they feel really uncomfortable dealing with ideas that are really beyond their frame of reference. And we really need to do that. If science is to advance, major advances come through revolutions, and revolutions come with some idea or some finding that was completely unexpected. Jacques was in that category, and not only Jacques, but I've been discovering in the past years that in many fields, there are many people who have alternative, quote-unquote, ideas. And some of them are flaky, but some of them are based on sound observations and evidence, yet it's difficult for those people to gain any traction because the way the scientific system is set up right now tends to discourage truly innovative ideas. And the reason for that is that the way the system works is if I have an idea that the Earth is round, but the prevailing view is that the Earth is flat. So I put a proposal in to get funding to pursue my round Earth idea. And the funding agency, who would, in theory, support this, what they do is they send the proposal to the experts in the field for review to see if my idea is crazy or sound or somewhere in between. And the experts are always the flat Earth people. So it means that the people who I'm challenging are the ones who review my proposal. You know, it's like in the French Revolution, Louis XIV judging whether the revolutionaries are meritorious or not.
Or the Federal Reserve kind of overseeing the system.
Well, yeah.
Kind of like that, yeah. Or the FDA overseeing the cures for cancer, right? You know, kind of like that.
Yeah,
but,
it really is like that. You know, it was set up in a way that made total sense because, of course, you want some experts to review proposals, but it doesn't encourage revolutionary science. It encourages incremental science, where, of course, you want to have the world's experts reviewing the proposals to make sure that the proposers are competent. But for revolutionary ideas that change the system, or attempt to change the system, like that of Jacques Benveniste and others, it doesn't work. It hasn't worked. If you ask yourself, how many scientific revolutions can you name, say, in the past 30 years? I'm not talking about technological revolutions because there have been a lot of those, the iPhone or Internet. There are many. But scientific revolutions that have succeeded, not promised to succeed, have succeeded in changing the world. Not many in the past 30 years or so. And I think one of the reasons is the one that I mentioned. It's like a court system where two people are sparring, and one of them gets to decide whether the other one is correct instead of a disinterested third party. It doesn't work, and this is a serious issue. I know this is not the topic.
No, actually, it's very much on point for the grounding of what we're going to talk about, because I did a piece on peer review, and I always grew up thinking peer review was it until I learned with Gavin Menzies, who wrote 1421, and a climatologist from Canada, how it really works, both academically and commercially. For publishing, I was shocked at peer review, and it describes exactly what you just described. But the whole inner workings of it, that peer review is not the it that we thought it was because of the process, the way it's put together, and you have people that have a stake in the way things are doing the evaluating. So you don't even get to know who's evaluating you. You don't even get to know what they think. In other words, that's all anonymous. So there's a whole part of peer review that needs a complete revitalization.
Totally agree with you. When anybody has a stake in the outcome, it's obvious that the evaluation is not going to be as fair as it would be when people who don't have a stake are making judgment. And, you know, now with funding levels, NIH, for example, a fraction of grants that are funded is somewhere 10, 12, 15%, sometimes even lower than that. So when you get down to that marginal level of funding where you need to put 7 or 8 proposals in to get one funded, the judgment is not as objective as it would be, or it used to be when the numbers were higher. You know, then it was easier to pick out the really promising proposals. Now, there are a lot of politics that go into it. If you put yourself in the shoes of a reviewer, it's very difficult to turn down your friend who you drink beer with. And then there's something that is even worse. There's a triage system. Perhaps you know about that. Many of the proposals that are submitted don't even get discussed. Unless they get high enough initial evaluation, the panel doesn't discuss it. So the proposer gets no feedback, except it didn't quite make it to the level of discussion. That's a really easy way to snuff out ideas that challenge the mainstream. And this is a serious issue. You know, the NIH was designed, I mentioned NIH only because it has a budget of in excess of $30 billion a year, and then there's the National Science Foundation, whose budget is much smaller, covers all of the rest of science. These organizations tend to discriminate against the truly innovative ones. NIH put together a discussion workshop. It was 6 years ago, I think it was, and it was called Fostering Innovation. That's really surprising, a workshop like that in an organization designed to foster innovation. Why? Haven't they really figured out what needs to be done? they're all sincere people. They want to do it the right way, and I think the administrators truly understand that there's a problem. They need to solve the problem. But as much as they'd like to solve the problem, the institution is so big that the inertia of the organization doesn't permit the kind of agility that you need. I attended this workshop. In fact, it was attended by many of the leaders of the different NIH institutes, Heart Institute, Cancer, and so on. And the director was present. It was a former director. And there was a panel of 15 people, including a couple of Nobel laureates. So it was a rather distinguished group. And there were two main speakers, and one of them was from a management consulting firm. And he spoke for 40 minutes and described what the NIH administration might do to improve the success in their mission. And the second speaker was me. And I had 40 minutes to speak to all those people. It was a really exciting day for me. And I brought forth ideas on what might be done to improve the system. And actually, a few of those ideas were adopted, although in a kind of marginal way. And most important is to make sure that the reviewers only consist of people who have no stake in the outcome. In the hallways, in the toilet, whatever, meeting various people, during the breaks, there was so much enthusiasm, even from the people inside the NIH, that really needs to be done. As I said, though, the institution is huge. There are forces that work against that kind of change, and so they don't move with great agility.
And particularly when you have large infrastructure invested in looking at something a certain way, dealing with something a certain way, solving it or treating it a certain way. I remember I did a couple interviews with Dr. Nicholas Gonzalez from New York, who's very well published and took his clinical trial of the enzyme treatment of cancer to the NIH. And his story is profound on what happened. So I think the transmission of ideas, that's its first line of resistance. But then when you have infrastructure supporting an industrial complex of something else, looking at it, we can say this about geology. Geology will not acknowledge the science of primary water, absolutely refuses at a university level. It would change everything. Anything that academia is looking at, this occurs. This orthodoxy is there. Look what happened to Rupert Sheldrake when he went up and spoke at TED. I mean, they censored him. They dumped his presentation to the bottom of the bottom of the bottom of their list because of what he said about the orthodoxy of science. And they called him a pseudoscientist and attempted to marginalize and attack him. Now, that's TED Talks.
It's funny.
Okay? They said their board of directors said that he is not a real scientist. Now, this is not a schlump. This is a guy who worked with all these people at Stanford Research Institute. They talk to each other, and we use remote viewing in our agencies. TED Talks is not even university level. Okay? It's just people sharing their ideas for 18 minutes. And look what happens, right?
It's designed to allow people to share ideas. But actually, in the case of Rupert, by the way, I was having dinner at his home in London 2 days after this happened, so we had a lot of discussion.
How propitious.
It's propitious. And it's had reverse effect because everybody knows about it, and everybody is now inclined to look at his presentation, which you can get on YouTube. So it's no problem at all. It had the reverse effect, and it had such a negative effect on TED.
The thing is that we have to vet things more carefully, I think. See, what Rupert Sheldrake did is he basically showed us where TED can't go any further.
Oh, yeah.
This whole thing made a huge contribution. Aside from what you said, more people became interested in his work, which was a positive. But it revealed the whole universe of discoveries that TED can't handle.
Yeah.
They can't handle it.
Yeah.
And so that's an opening for other opportunities and people to start their version and to take it from there.
Something positive needs to be done. And,
yes.
We're actually working on something that may happen in the future, a kind of institute to encourage promising ideas that challenge current conventional thinking. And perhaps you may be hearing about this in the future.
I may be closer to it than you think. And I'll tell you more about that as this goes on.
Okay. Well, yeah.
All right. Well, listen, let's go right to some of the science of water. And I'd like you to share the frame of reference that is your main precept in the book, The Fourth Phase of Water. I know it's extensive, but the main precept about the exclusion zone of water. What is it? Why is it important? Tell the audience. Give us the frame of reference.
Okay. Exclusion zone is a name that was given to something by us because it excludes. It's a zone that excludes. Everything that we've checked particles and solutes down to a very small size, and apparently this zone is able to exclude it. But that's just a kind of sidelight. It's called exclusion zone because of that. What we found is that water has 4 phases, not 3 phases. Now, we all learn in school that water has a solid phase, which is ice, a liquid phase, which is H2O, and a vapor phase, which is humidity that we experience, water vapor. We found that that's not true, that there's a 4th phase. So what is this 4th phase, which we call the exclusion zone because it excludes? The 4th phase happens or occurs or builds when water, H2O, sits next to particular kinds of surfaces. Now, it's most surfaces, but primarily the surfaces need to be so-called hydrophilic or water-loving. You know the difference between hydrophilic, hydrophobic, water-loving, water-fearing. So if you have a surface and you put a droplet of water on it, if the droplet spreads out, it's called hydrophilic, water-loving, because the surface loves the water, so it clings to it. But if it's hydrophobic, then if you put the drop of water on the surface, it beads up. It doesn't like the surface. So we're talking about water next to hydrophilic surfaces. When the water meets a hydrophilic surface, something amazing happens. The water changes its character, and the change is not just at the very narrow surface layer, just a few molecules that touch the surface, but it propagates way out into the H2O. It can propagate easily by 0.5 millimeter, and sometimes we've actually seen a meter in certain unusual cases. So it's pretty extensive. So this is a kind of water that's different from ordinary water. It's like a crystal. The water molecules are somehow rearranged into what we think in ordinary so-called bulk water, H2O, is random. But here it's not random. It's all lined up. So it's kind of like a crystal, something like ice, but not hard like ice. It has the consistency of a kind of gel, like raw egg white or something like that. So we have this zone, the so-called exclusion zone, because it excludes everything, sitting next to hydrophilic surfaces. Now, the surface could be really extensive, a meter long or 0.5 meter long, or it could be even a molecule, because these molecules have charge, and if they're sitting in water, then one of these exclusion zones, or 4th phase water, we call it, will build next to it. So it's all over the place, and it's also particularly in your cells. It's in your cells because your cells are just filled with these hydrophilic surfaces. All the proteins and the nucleic acids, they have charges on their surface, and these charges make at least regions of those molecules hydrophilic. And so we have this 4th phase water that's in your cells, and it's probably most of the water in your cells. You think of your cells as rich with water, so we're all 2/3 water. But if you think of it in terms of the fraction of your molecules, the water is really small, so to make up that 2/3 volume, you need a lot of water molecules. And it turns out, if you make the calculation, that more than 99% of your molecules are water molecules. Your body is just full of it. But there are 2 important features of this water that I need to mention, because that's where the implication for science and health comes. The first is that this region, this 4th phase of water, is not neutral. It's actually generally negatively charged. And so this 4th phase water is negatively charged, and equal and opposite charge lies in the H2O, in the water that's just beyond this exclusion zone. So it's kind of like a battery. The exclusion zone is negative, and the region next to it is positive, plus minus battery. Usually, in order to charge a battery, your cell phone battery, you charge by plugging it into the receptacle, but there's no receptacle handy. So the question is, how does this water build? In order to build order, you need to put in energy. So where on earth does the energy come from? Well, we found it comes from light. And when I say light, I mean not necessarily visible light, although that certainly does it, but I use light in the more general term. That would include UV light, infrared light, and perhaps, we don't know yet, other wavelengths in the electromagnetic spectrum that are either longer wavelength than light or shorter wavelength than light. That's where the energy comes from. So the light comes in to this system of water next to a surface, and the energy contained in those photons in the light, that energy is used to build the exclusion zone and separate the charge and create this battery that we have. So there's a lot more to it, but you asked me to describe
sure.
the basic fabric, and I guess that's the basic fabric.
So this is not just something that you've identified. It's a demarcation, is it not? Is this a new direction for water?
Oh, absolutely.
Talk about the implications of this.
First, new direction. There were various suggestions over the years, starting 100 years ago, that water might have some kind of distinct phase that's different from the ordinary H2O. By the way, I didn't tell you, this is actually not H2O, it's H3O2. So it's, you might say, chemically different from water. We call it water, but it's actually not really water. So there were people along the way, including, for example, the father of modern biochemistry, Albert St. Georgi, who won the Nobel Prize for discovering vitamin C but did many things beyond that. He knew that the ordered water was really important for all of nature. He didn't quite get to lay out the details of it, but he knew. And then there was Gilbert Ling, who's, I think, about 95 years old and still active, who proposed in 5 books that the water inside the cell was organized, structured. And he was a kind of mentor for me. He was the first to awaken me to the idea that ordered water is really important in nature, particularly in biology. The general concept is not entirely new, but the details and the way it works and the fact that it's a battery and the fact that it's driven by light, those are all new, and it changes completely not only how we look at water, but it opens the possibility that many of nature's workings may operate in a similar way. So it's a fundamentally new paradigm. You know, if you read the chemistry book talks about reactions. You put 2 reactants in a vessel and they react with one another. Well, if this is sitting in water in an aqueous solution, the chemistry books contain nothing of what I've said. But if what I've said is true, and of course I think it's true because we have so much evidence, is necessary to re-examine the interpretation of practically every reaction that occurs, because light is involved, particularly infrared light, which is all over the place. We receive it from the walls, the desk, the people. You can't get rid of it. It's all around, and that's very important for building this phase of water. So the chemistry books and the biology books, they have nothing of the fact that light is really critically involved, light in the generalized sense, and that you have a zone of ordered water, structured water that has charge, an opposite charge in the liquid, the water of the solution. So these are new concepts, and these new concepts, I think, need to be taken into account in any interpretation of any chemical reaction or physical reaction taking place in water.
Do you agree that the physics of water and the chemistry of water are different universes of conversation and discovery?
Well, they shouldn't be, because, I mean, where is the borderline between physics and chemistry? It's really hard to define.
I'll tell you what I mean in my very limited understanding. Someone said to me, there's a distinction between taking fluoride out of water as a chemical and removing the frequency of it. Where are you at about that conversation?
Well, okay, it is difficult, but I think it's true. The physicists and the chemists speak a different language. Physicists talk about energy, they talk about quantum mechanics, and the chemists are mainly dealing with reactants, and periodic table is rather ancient, but that plays into what they do, and techniques that are seemingly mostly chemical techniques. So there is a kind of divide between the two, just as there is between biologists and chemists, although biology is really nothing more than applied chemistry and physics. So, yeah, it's true that in terms of the fluoride that you mentioned, the chemists would be approaching this as what chemical reactions might occur in the presence of fluoride. And the physicists, well, you're talking about information and signals, but I think a lot of physicists would deny any such subtle effects. Most physicists are maybe more conventionally oriented. On the other hand, the topic that you allude to about signals is gaining more and more people who are getting serious about this issue. And at our recent Bulgarian meeting, I'd say 1/4 of the presentations dealt in some way with electromagnetic signals and how they impact water. There's a lot going on. But this is not well known to the standard physics community, and most physicists would react by saying, well, this is the biggest nonsense I ever heard.
You know what's interesting, though? When I started It's Rainmaking Time in Burbank in 2004 for radio, one of the first few shows, we had a bunch of scientists and people in the area of water from all over the world, by the way.
Yeah.
And some of the people had created this vortexing water technology for agriculture.
Yeah.
And they were testing it to see how it changed the flow rate or how well it grew, how much it grew, how rich it was, etc. And over the last 10 to 14 years, I've talked to many people across the world who have different types of technology that do incredible things that is on a physics level different, but at a chemical level, you can't prove the chemistry of it. Like I had Clayton Nolte on. He was formerly with the Electronic Warfare Division of the military, and he has something. I had Dan Nelson, who, by the way, I invited on this conversation because I wanted him to ask you some questions from a physics point of view and from a chemistry point of view, and I'll bring him on in a few minutes. So we know that there's a something with this in the physics area, and I have a feeling that you're alive at this time in history to bring all these integrated pieces, and some of the other people on the earth are here to integrate a lot of things that were not able to be integrated before because there's such excitement and passion and a real commitment to do this. And I think you represent one of the people that is an integrator, and even though you have your own discoveries, I don't see you coveting. I mean, I don't know you, I can't say that, but I don't see you coveting this. I see you opening it up. Am I right or am I wrong?
You're absolutely right. That's reflected in the meetings that we have. I organize meetings each year on water, and I invite diverse people with diverse points of view and interesting observations in all fields that relate to water. We want input. As you say, we want to integrate all this input and try to understand what it means. So, yes, absolutely. And regarding the point that you made about, I guess now I'm kind of realizing more about the distinction you were pointing to chemists and physicists. Sure, the chemists would look at water and say, well, basically it's H2O, so no matter what you do to it, unless it has impurities in it, we have to check the impurities because some of the impurities might be dangerous. So if it's free of impurities, then it should be okay. I guess that might be a chemist's point of view. And I think the physicists would look at it a bit differently, and considering the possibility, at least, that some energy might have an impact on the water. And that's really what we found, and I think maybe that's the reason why physicists seem particularly interested in this. In fact, the editor of the physics journal Entropy just asked me to edit a volume that deals with the fourth phase of water. So there's a lot of interest from physicists.
Fantastic. First of all, I wanted to invite in our other guest today, who's a very prominent theoretical physicist. He is the founder of the Positron Group, the maker of Wayback Water. I told him that you and I were doing an interview today, and I asked him to please join because, Gerald, you're too big to take on alone. So, ladies and gentlemen, welcome Dan Nelson to It's Rainmaking Time. Good morning, Dan.
Good morning.
Thank you for being here. And Dan, meet Gerald Pollack, the great
Hi,
Gerald
Dan.
Pollack.
Okay. Good to meet, quote, unquote, meet you. Yeah.
We're virtually here. I want to say one last thing about what we were talking about, Gerald. We just had on Sherry Edwards, who's in Ohio, who does bioacoustic vocal profiling. And she's been working on this for years, and she actually works in the area of the voice. So you can use frequencies with voice and actually help people eliminate their diseases. So this is using frequencies in a different way, another kind of science. It's a different thing than water, but it has really to do with the question of chemistry and physics. And so I'd like to ask Dan if you have any questions or would like to bring up anything that Gerald has talked about or I've talked about or anything you want to add.
Well, to begin with, there is no way I would intend to be confrontational here because he and I are playing on the same team. So to speak. Maybe he's in center field and I'm in left field. But,
how humble, my God. That's the kind of guest we want.
Well, the World Series is going on. I thought that was appropriate.
Oh, indeed.
Anyway, I guess my ideas are fairly radical, but, there's an old saying that proof of the pudding is in the eating, and I have successfully engineered water based on a theory that's radically different.
Yeah.
there have been tests done on the water, and a PhD in microbiology said that today we are seeing water do something that nobody in history has ever seen it do. And my emphasis was on actually getting water across the membrane wall of the cell efficiently. So my theoretical work in water spawned a paper, and this gentleman asked me not to mention his name, but he was prominent in the efforts to detect water on distant worlds. He read the paper, thought it was fantastic, and said if what I was saying was true, this could be a Nobel Prize, which I'm not interested in a bit.
Why not?
But my work is pretty controversial, so...
Well, that's good.
That's why we're here, folks.
What I would say is I have an idea, and this is just a harebrained idea of why water assumes the fourth phase that it does.
Okay.
And it has to do with the fact that years ago, this is typical of some knothead physicists, particularly me. We ask some of the dumbest, simplest questions you can imagine. And I started out with a question. I wanted to know why water has the density it has, why it's between 1,000 and 1,500 times denser than the atmospheric gases, and why you can compress atmospheric gases to several atmospheres of pressure and the weight is still negligible, and why a bucket of water is so much heavier than an equivalent bucket of compressed air.
Yeah.
What came out of the theory was that water does not exist as independent, unattached, free to move around H2O molecules. Water is always a crystal. They form little tiny three-dimensional symmetrical crystals called polyhedron.
Yeah.
My work focused on engineering I call those water particles, the size of the water particle. So I guess I'm the first to actually say that water is not H2O and H2O is not water. Going back to something you said earlier in your discussion, I think one of the biggest problems in science is that we make assumptions that may or may not be true, and we set on them with all of the weight we can muster, and we refuse to move off of those.
I know it feels comfortable to have a frame of reference, even though it's wrong, but a comfortable frame of reference on which you can build. That's not, unfortunately, the way to reach truth. In our case, we try to dig down beneath those assumptions and test those assumptions, and I've found that many of those assumptions are actually wrong. Probably you agree with me. We've tested a whole bunch of them, and if you look in the literature, it turns out that practically any scientific paradigm or law or whatever is violated, and there are people who actually recognize that, but these people are in the great minority, and the majority of people don't like to acknowledge that they're being challenged. It's more comfortable to just ignore those people, and it's really easy because you can simply declare them a crackpot, and, this is pseudoscience, so to speak, and then they get nowhere. So we agree on that about the assumptions that this is a real danger. It's a kind of fragile bridge that we walk on, and the bridge can easily collapse.
That's right. I suggested that nobody in history has ever seen the components of water interact, which is a problem in and of itself. But,
I agree with you. Even things like the boiling point and the freezing point, it turns out there's no freezing point. It depends on conditions. It could be 0 degrees Celsius or sometimes minus 20, minus 40, minus 60 or whatever, depending on conditions. And a guy at Cambridge University, Hasek Chang, I'm not sure if you know him, showed also that the boiling point is not a constant either. It also depends on conditions. So some of the things that we assume are there and okay are not so okay. I just want to get back to a point you mentioned about H2O. It's very interesting what you said, because nobody really has put forth an acceptable model for bulk water that satisfies all the data and all the evidence. So your idea is interesting that in bulk water there are crystals, and at the recent Bulgarian meeting, there indeed was a presentation that demonstrated, especially in homeopathically diluted preparations, that there are particles that appear, and these are submicron, 500 nanometers or something like that. He called them water aggregates, and he tested these using a light scattering method, which can measure the size of particles that are suspended in the water. So he called them nano-associates. They consist of water and some other molecule, but it's basically a cluster or so, similar to what you were talking about.
I simply said that the simplest and easiest mistake to make was to say that H2O is water. But if you slightly modify that statement and say, no, actually H2O is the construction component or building block of water. To get the density, you have to explain why they come so close together, and my work tells me that the water molecule is actually a boson particle with a spin of 0.
Explain what a boson particle is.
Well, it would be a symmetric particle, and in quantum mechanics we have particle exchange rules, and it meets those rules. Any boson can be exchanged for any other boson. You can't do that like with a fermion. An example of that would be an electron. That's an asymmetric particle. And the bosons would have an even spin integer like 0, 1, 2, etc. An electron has an odd spin integer of like 1/2. A fermion could have a spin integer of 3/2. But the point is they're weakly interacting, so they are gregarious. They don't mind coming very close together because they don't react with one another. And when the H2O molecules do that, the fact that it's slightly magnetic and the Coulomb field actually guides these particles into symmetrical crystals. Then it becomes a thermodynamics problem. How big is the water particle, and will it go across the membrane efficiently? Well, it turns out in the test done by a microbiologist, these are standard absorption tests. We just put cells on a slide under a microscope, put water on, and see how long it takes those cells to hydrate. Well, just about any water purified in any way you can imagine will take actually hours to show signs of hydration. They actually watched my water go across the membrane wall, and they watched the cell plump up in a mode of total hydration in 10 seconds.
Wow. Wow.
He couldn't believe that. He said, well, this strains credibility. He says, we've got to do this test over again. Something went wrong. Well, he got the same results every time. I'm not supposed to mention the name of this university because there's an unfunded study going on. And it was a favor to a fellow faculty member who wanted the water tested. But this university sent us a preliminary report, and they are incredibly impressed. They're calling it magic water. I actually had to call and say, please don't call it magic water. That's got the wrong connotations. This is a legitimate scientific effort on my part and legitimate scientific inquiry on your part.
What kind of water are we talking about?
The water I engineer, I developed a unique laser 25 years ago, and I found out how to pump energy into the system of water, bulk water, and the water particles will actually disassociate. They'll come apart immediately, reassemble as smaller particles with a different geometry.
Yeah, I see.
You know, I noticed you talking about giving a talk on a YouTube video about the fourth phase of water, and you mentioned that you might test some different waters, and I certainly hope you'll take a look at this water.
Well, I'd like to if you send us some. We're actually right now testing hydration of different kinds of waters, because I agree with you. Hydration, of course, is so critical for health. There was that book published some years ago.
Dr. Batman Jelly, Your Body's Many Cries for Water.
Right.
I love him for what he did.
I do, too. This is amazing. You know, in all his clinical experience, he just told everybody to drink water and get better. He didn't really talk about different kinds of water, but I think different kinds of water should hydrate better. And this may be the ultimate reason. When you think of water as improving health, the ability to hydrate, as you mentioned, may be absolutely critical. Sometimes you can drink water and it doesn't do anything, but other kinds of water will really hydrate. I had thought that the reason was that some of these waters contain EZ water or fourth phase water because this water separates charge and therefore has a big dipole moment. So you have it like a beam with plus minus, and the cell is negative. So this plus minus, when you expose it to this negatively charged cell, the positive will orient toward the negative cell and get sucked up quickly. That's what I thought might be the mechanism, but, you know, that's conjecture at the moment. Perhaps your ideas are closer to the truth.
What is your idea, Dan, about how to hydrate the cell? You talk about getting the water into the aquaporin channel, but explain to Gerald what you're talking about.
Well, this is a smaller particle size. What the microbiologist observed was the osmotic pressure of the cell was literally sucking the water through the aquaporin channel until the amount of water was sufficient, and then the cell knows when it's got enough and quits hydrating.
I see.
You know, when I go out and teach, I'm saying that I don't think there's a potable water on planet Earth that you can efficiently hydrate on. I set about to engineer it.
Yeah.
It is engineerable.
Dan, your water is used homeopathically. You don't just get a bottle and drink the whole thing down. Explain that part, because that's a missing part of the conversation here.
Well, yeah, people in the past have made the mistake of getting the water and starting to slug down as much as they feel like drinking, and the next thing you know, they're going through a doozy of a detox.
Yeah.
Yeah, when those cells can efficiently hydrate, their first priority is to purge. So there's a ramp-up schedule you follow to minimize. Even at that, there will be, in some cases, a mild form of Herxheimer effect, but nothing serious. But that's one of the considerations. And also, now, this is going to change the tone of this conversation, but I am absolutely not the kind of person to stretch the truth or lie. I was involved with a project where we actually made gold nuggets appear in a tank of water by putting 13 frequencies in the water, and the gold simply materialized. I'm absolutely telling you the truth, totally telling you the truth. You can call it alchemy or you can call it quantum mechanics, but it begs the question, what is a particle of mass? I believe it's a waveform structure, very tiny in vacuum space.
Yeah.
And if you get the right waves into vacuum and they start interfering with one another and knitting together, you've got a particle of mass.
Okay, yeah.
I think we're talking about the fifth stage of water.
Amazing.
Or the 4+ stage.
You know, there's actually been a lot that's not so recognized on the issue of transmutation. I don't know if you know about the work of Louis Kervran.
Yeah, I do. Mm-hmm.
Okay, yeah, and other people have followed up, but of course this is labeled alchemy, and it falls between the cracks and is not considered to be acceptable research. You're labeled as a kind of a quack doing pseudoscience. But what you say is interesting. Have you published this at all or reported this? It's so interesting.
No, because you're kind of trying to anticipate and look ahead in time to what the reaction will be, and you're not real comfortable with what you think it'll be.
We're talking about Jacques Benveniste, so we have a clear example of what could be.
Yeah, and I'd like to suggest to you that I edit the journal called Water, and your observations involve water. And I would like you to consider the possibility of submitting your paper to a very open-minded group of reviewers and publishing your stuff in our journal. We would welcome it.
Woo!
Okay, yeah.
It's rainmaking time. It's on. Can I ask you both a question that I talked to another scientist about, and he started talking about this, and all I could do was write a few sentences. He said, a lot of water scientists and pioneers are aware of something called the hydrogen bonding angle of the water molecule. Something about the hydrogen bonding angle of the water molecule is a key also to where the action is. Does anybody have anything to say about that, or am I also in the left field beyond the left field?
No, you're not in left field. If you look in any chemistry textbook, it has a picture of the water molecule. There are certain preferred angles of the hydrogen bonds, and I guess that's what they're talking about. There's a generally accepted angle. I forget what that
Well, apparently
is.
There's some type of coveting of knowledge that's pretty impactful about water in this area. And I don't know if you know that or you talk to other people or people are kind of closed-mouthed about this.
Well,
But if not, then that's fine.
Okay.
It's unknown. How about you, Dan?
That's what I'm manipulating with the laser. Bulk water starts out with a bonding angle of about 109 degrees, and I'm cranking that bonding angle out to 122 degrees by pumping energy into the proton. And I increase the strength of the electrostatic field or the Coulomb field around the two hydrogen protons in the H2O molecule. They repel one another, and we can force the bonding angle to widen, and then the entire particle has to come apart and reassemble as a different-sized particle with a different geometry.
Ladies and gentlemen, that was Spock from the Starship Enterprise. I wanted to ask you, Gerald, first of all, I love the examples in your book. So many examples that you bring home about our joints, about coffee, where does the vapor come from. You say that any surface that touches water will have some effects. The container, suspended particles, or even dissolved molecules.
Right.
What do you mean by that? Explain that. I thought that was very, very interesting.
The point was that this exclusion zone or fourth phase used interchangeably, if you put a particle in the water, if it's hydrophilic.
Water-loving.
Water-loving, yeah.
Okay.
If you have water-hating, hydrophobic, the particles won't suspend themselves in the water. They'll just cluster together and drop to the bottom. So the only particles that easily suspend themselves in water are the hydrophilic ones. Now, around each hydrophilic particle, we found there's a spherical shell around it, and that shell is easy water. And that's usually negatively charged, and therefore the region just beyond that in the water in which this particle is suspended has positive charge. And probably the reason it's suspended is because you have a negatively charged, basically, particle in a sea of positive charge. So it kind of sits in a stable position, and that's why it's suspended. Now, so it's difficult to tell what happens when you get smaller to the size of a molecule, because then the instruments are not so easily available to test that. But every particle that we tried that's suspended in the water, we found that from big ones to small ones have this shell of easy water. And so we can project downward to very small particles and solutes that are suspended or dissolved. Really, the distinction loses their meaning, because when you're sitting at the boundary between a particle and a molecule, where exactly is this this distinction? It's kind of fuzzy. So anyway, it appears that everything that is in water, either suspended or dissolved, has an EZ around it. That's really what I mean by impacting or affecting the water. And it depends on how much energy is coming in. So what Dan was just talking about the laser. So I think that it's possible, in the framework of our paradigm, it's possible that you put the laser light in, and the laser light builds this exclusion zone. And I would say that there's a possibility that the way that this works is that the laser is actually building more charge separation, building more EZ, and possibly that's the reason why it hydrates better, because you have more charge separation, and therefore with these bigger dipoles, the water gets sucked into the cells more quickly. There are a lot of people who are using lasers or optical sources for one thing or another, even for blood flow. There's a company called Beamer, B-E-M-E-R, and they've demonstrated that you expose the patient to a laser, and I can't remember what wavelength, and the blood flow speeds up miraculously just by a little bit of local light. So the light has a really important effect. And other scientists, there's a fellow, Benny Johansson from Stockholm, demonstrated that you take some water and basically just expose it to light of various kinds, and he finds after an exposure of a day or two, the solution, the water, has completely changed. So I think there's a lot of evidence that supports, Dan, your point of view, and this works also especially in homeopathic dilutions. That was shown at the recent water meeting, that if you take these dilutions, there are actually little particles that form inside the water. With the third or fourth or fifth dilution, these particles get, or nano-associates, get very big. And then more and more dilutions, they get smaller, just like benveniste would have shown. And then they get bigger and smaller. There's a kind of oscillation depending on the number of the homeopathic dilution. So I think it all is kind of beginning to fit together into an understandable paradigm that light has a big effect on water. And it's just the same, in a way, as what happens in plants. You know, plants photosynthesize. They get light, and the light is their fuel. And step one in photosynthesis is the separation of water into positive and negative components. Of course, there are many steps that go beyond that, but that's the first step. And the paradigm that we've been demonstrating is so similar to that. It's a kind of generic first step in photosynthesis, in that the light is separating the positive and negative components of the water molecule. Of course, the plant does it better, and the chromophores that absorb the light are more efficient in doing that. But I think the principle is pretty much the same.
I have a question for both of you, starting with Dr. Pollack. When you're doing your clinical testing on water, are you keeping notes on what's in the water? In other words, what are the chemicals in the water that you're testing?
We haven't done any clinical testing yet.
Okay.
However, when we do it, which I hope is soon, because it's so important to do this, of course we'll keep track, as you alluded to, from the chemist's point of view.
Yeah, but I think it's relevant in both paradigms, right? In pure and regular academia, where they are right now, where everything is, and to take it further to at least have the frame of reference. So let's say you have X number of milligrams of fluoride and X of chloride and X of whatever else is in there. So when people are testing water, yeah, it's the same solvent, but it doesn't have the same stuff in it. So you can compare apples to apples. I just wanted to bring that up. What do you think about that, Dan?
I'll tell you a story. I was getting calls from Australia. When they give medications to the elderly, they actually take the medication and they put it into one of these ultrasonic devices. A frequency goes into water, and then it breaks up the medication. Then they drink the medication. They were thinking about using my water, and I said, no, you'll have to readjust the dosages of all the medications because this water brings things into the cell much easier, which is why you wouldn't want to use fluoride water or water with chlorine. So when I engineer water, I need a pure source of water.
Yeah. You know, one of the things I was thinking of as you were talking about hydrating the cell, we found in many instances that the behavior of the cell is just like the behavior of a gel. And the gel has no membrane. The cell has a membrane. And, for example, if you measure the electrical potential difference of the inside of a cell to the outside of a cell, it is sort of commonly known. It's 100 millivolts or 80 millivolts negative. The surprise is that if you stick the same electrode into a gel, which has no membrane, you get the same result. Now, the textbook teaches you that it's the membrane that's responsible for the electrical potential and so many other features of the cell. But the odd thing is that when you investigate an entity that has no membrane, it behaves in a rather similar way. So it's kind of hard to put the emphasis on the membrane. And, when we talk of hydration, we think of the membrane as being the limiting factor. So what I was wondering and going to ask you is that it might be interesting for you or anybody who's studying hydration to study hydration in cells and hydration in gels. Gels also, the dry gel absorbs huge amounts of water, sometimes as much as 20,000 times their own weight. So it might be interesting to compare because that's not to detract from the evidence that your water hydrates the cell better than other kinds of water, but just to figure out the mechanism. Because if we're talking about the membrane as a limiting factor, and then you get similar results in a gel that has no membrane, that raises some question. There is evidence, this was in my previous book, not the fourth phase of water, but cells, gels, and the engines of life, that the membrane is really less important in the cell than we think because there are examples where you can break a cell in half, literally in half, and the cell still functions fine. So it raises the question of how important really is the membrane around the cell. The idea of membrane came because if you think of the cell as a liquid, in some sense, you need a container to keep it all together. And it looks from the electron microscopic evidence that something is there. However, if it's a gel, which I think it is, there's a lot of evidence, and all you have to do is feel a cell, and you can feel that it's gel-like, then you don't need a membrane. I'm not suggesting that the membrane is absent, but there's a lot of evidence that the membrane is not really a continuous barrier that is impermeable to virtually everything, except what goes through the channels or pumps and whatever. I think that paradigm needs revision. I think the membrane is actually leaky, and things can pass through readily. So, when we talk about aquaporin channels, I'm not so sure that they're really the limiting factor. I guess that remains to be seen. Anyway, I just wanted to mention the idea of checking gels as well as checking cells.
Oh, that would be very interesting. What do you think, Dan?
That is an interesting idea, and that does have to be tested. Yeah.
I wanted to ask the other question in the book, The Fourth Phase of Water Beyond Solid, Liquid, Vapor. You say water is a universal attractor, like attracts like. It's also attracted to light. But what do you mean water is a universal attractor? Can you expand on that for the audience?
Perhaps I worded it too loosely. I will expand on it.
Thank you.
Suppose you have two negatively charged particles, and you pull one from your right pocket and another from your left pocket, and you drop them into a glass of water so that they're pretty near one another. And if I ask you, Kim, what do you expect would happen to the distance between them? I'm not sure, but probably you say, well, they're both negatively charged, so obviously the distance between them will increase, right?
I don't know that I would say that. I think I would need to go take some medication to figure out how to answer it.
Okay, well, the answer has been known for 100 years.
Well, see, what do I know? I shouldn't even be doing this interview. Go ahead.
Well, I didn't know it either, but But I learned from the great physicist of the last half century, Richard Feynman. Well, the answer is that they actually come together instead of repelling. And this was known even before Feynman, and Feynman called it like likes like. That is, two like charges like each other, and things that like each other come closer together. So he said like likes like, and the reason like likes like is because of an intermediate of unlike. So if you have two negatively charged particles, you get positive charges in between, and those positive charges draw the two negatives together. So like likes like because of an intermediate of unlike. But it wasn't clear where those positive charges came from. And I think we found the answer, because when the exclusion zone forms, the negative exclusion zone creates protons all around, and those protons are in high concentration between the two particles, so they act as a draw. So if you have two like particles, they come together. And of course, if you have like and unlike particles, they also tend to come together by the usual mechanism of attraction. So it looks like it doesn't matter whether you have minus and plus or minus and minus. They all come together. So it looks like water is a universal attractor. It's a very nice thought that, everything likes everything else and comes together instead of hating one another and drawing apart. So there's maybe a philosophical implication.
How about water is friendly? Water is love.
I
Water
think
is
that's
life.
fine.
Yes.
Water is love. That's better.
Yeah.
I like that.
Now, I want to ask you both, starting with you, Dan, what is your take on the effect the magnetic field has on water? And is water magnetic? I know I asked two different but connected questions, but good luck, and it was nice to know you.
Yeah, water is magnetic.
Why do you say that?
Because of the way the H2O molecule is structured, and goes way, way back to the work of a German physicist named Arnold Sommerfeld. Oxygen is going to want to have 8 electrons in its outer orbit. Any two substances, when they come together and form a bond, they're going to want to fill the outer orbit. And if it's not filled there, it's not in its most stable energy configuration. So the oxygen side will have a slightly negative charge, and the two hydrogens are not that far apart. So that side will have a slight positive charge. But in my work, when the particle gets formed, the negative charges, the oxygen side gets, as it were, locked into the center of the particle, and the positive charge gets locked onto the periphery. So the hydrogen are outboard, the oxygen is inboard. That has interesting implications for the fourth phase of water. Well, this is strange. If you got just a minute, I'll share something with you. I've done the theoretical work on this, and there's a prototype being built now, and I'm pretty sure it'll work. It's not a very big object, and I noticed one of Dr. Pollack's lectures, I think it was his interview with Dr. McCullough, and he mentioned seeing dust particles floating around in the air in a room. He had an interesting explanation for why they don't just all fall to the ground. Gravity doesn't pull them down. I'm developing an object, and it's based on a hexagonal structure that looks like a bee's honeycomb made of metal. It goes back to what we discovered in the quantum field theory, where the vacuum, which is all around us and everything, is understood to be a chaotic sea of practically limitless energy, with an energy density equivalent to about 10 to the 94th power grams per cubic centimeter. In other words, there's, for all practical purposes, an infinite amount of energy locked up in vacuum space. That's at the quantum relativity level. But going on in the vacuum medium, there's an incredibly large destructive interference of virtual particle wave functions. And physicists have actually wondered why the universe, because there's so much wave activity in vacuum space, why the universe doesn't destroy itself. It turns out it's because of the fact that there is interference of waves with other waves, and they cancel one another out. Otherwise, it would seem that the vacuum state would get out of control and virtually destroy the universe. But in my work, what I've discovered is that you can actually stimulate or excite a particular frequency in the vacuum medium. This object was designed to do that. It'll take really tiny particles like dust particles and act like a Cuisinart and just break them up into their constituent atoms and molecules.
Can you tell us how this connects to water and why you're giving this example?
Well, because what he's finding is the fourth phase of water has a hexagonal structure. I believe what's happening is inside the cell you would have constituents such as the proteins, in particular the nucleic acids. They're relatively vulnerable and sensitive structures, and I believe the water is in there as a protective mechanism, because it's true that every particle of mass interacts with vacuum space around it and draws energy from it, but there would be interference activity in the vacuum that you would not want those sensitive structures exposed to, and that phase of water would do an extremely good job, like in the reverse state of what I'm developing here. It would have a tendency to protect the sensitive structures, the proteins and the nucleic acids and so forth, from potential for harm from certain vacuum space activity.
What do you think about that, Gerald?
The idea protect is interesting because Albert St. George used almost exactly the same words, that the structured water around the proteins and the nucleic acids could protect those structures. I don't know that he was talking about vacuum space and energy, but the idea of protection was there. It forms a kind of protective sheath. But I just want to comment on your question, Kim, about the magnetic field and water, because there has been a lot of work, apart from the theoretical point of view that Dan was discussing. There experimental work, which is really undeniable. So the story is, 6 years ago, I invited a guy who suspended frogs in magnetic fields. And I invited him to the meeting, our water meeting, because I thought, hey, this is really cool stuff. And his name was Andre Geim. And he told me that he's not coming to our meeting because he changed fields. And 6 months later, he received a Nobel Prize in graphene. So I understood. So I've been trying to recruit him to come to our meeting, but he's too busy with graphene and actually with staying home from meetings so he can actually do research instead of being shown off as a Nobel laureate.
Do you think you could talk him into levitating some of our global leaders and keep them in suspended animation? I think it would be really effective, and since he can do it with frogs, I think it's just a question of density, yeah?
Well,
yeah.
I have some friends who claim to levitate, and I haven't seen a demonstration yet, but I am going to the university in May where they teach that sort of thing, and I'll be curious to see what I see about.
I want to hear back from you. Don't you run away. But you were in the middle of saying something important, and I cut you off with that comedy. No good. Go ahead.
Well, yeah, so, Andre Geim showed the same thing. Instead of frogs, he said, well, it's the water inside the frogs. Someone else showed that even rats levitate, or mice, but water also levitates in a magnetic field. So there's definitely a strong force that occurs. And maybe the most or equally vivid demonstration was a Japanese professor, I forget his name, from University of Tokyo, and he showed in one of his presentations a film of what happens when you put a superconducting magnet near water. So he has this tank of water, and for reasons that will be obvious in a moment, he put some red dye in the water, so the water is red. And then behind this tank of water, he has a superconducting magnet, and he flips the switch, and the magnet goes on, and the Red Sea splits. So you could really walk through it. This is an amazing amount of force. And there was another Japanese investigator who studied effective magnetic fields on colloids, similar to some of the colloids that we have in our body. He spent 10 years. He has so many results published. There's always an effect of magnetic fields, and he quit because he couldn't figure out what the mechanism was, and he went on to study something else. So definitely magnetic fields have some effect, and it remains to be seen what the mechanism is, but these dramatic illustrations leave no doubt about the effect.
You know what would be very interesting is to take magnetite in whatever tests you're doing, Gerald, in Washington, and do some of the testing with the exclusion zone and magnetite surrounding the water and see what happens to the water molecules.
That would be interesting. Thank you. I'll put that on my list.
I interviewed one of the scientists in New Mexico who did a lot of work with that, and also with gold, actually creating gold out of thin air. And he was the one who did a lot of work with that. But so I think the combination of what you're all doing, I think we're going to be in the inclusion zone by next year. Do you have any other questions or comment you'd like to say to each other?
Well, I wasn't aware of your work, and I would like to find out more.
Well, that's great.
Yeah. I feel that his work is the most significant thing that's been done in biology in a long time.
Well, thank you.
It'll go on to be the most significant thing.
Well, I'm delighted. I'm delighted to have you both on, and I know that the audience is going to be scratching their head, as I have during some of the conversation. I actually had to walk away and come back a couple of times just to make sure I was still on the earth listening to both of you. But it's so interesting, and I know that the work you're doing is going to take us to a whole other level regarding water. And I just want to thank you, Dr. Gerald Pollack, for your book, The Fourth Phase of Water, Beyond Solid, Liquid, Vapor. And for those of you who would like to find out more about Dr. Pollack's work, you can go to faculty.washington.edu/GHP, and you can find out about Pollack Laboratory. To find out more about Dan Nelson, you can go to the Positron Group and also waybackwater.com. I want to say, gentlemen, that I'm so impressed with you, and to me, you're such giants in the field that I was wondering if you would come back. And what I'd like to do is to invite Dean Bonley, who's a kind of world-renowned in the area of magnetics, and have him join us, and maybe one or two other people, and return in 3 to 4 months. How would that be at the new year?
That'd be great.
Thank you so much. Ladies and gentlemen, it's rainmaking time. We have been with Dr. Gerald Pollack and Dan Nelson. Thank you for being here. Thank you both, gentlemen.
Thank you.
Thank you.